that question served as a little breather as well, because we're on to now some more complicated stuff. So we have this question here. So there's a resonance structure for the peptide bond below that we want to be able to draw. So they give us this peptide bond here. So if I drew it out, it'd just be, as they wrote, H3N attached to a carbon. Okay, that's a carbon chain, and this attached to another carbon, which has an O up top. Okay, another nitrogen, hydrogen, carbon, and then COO minus. Okay, so this is what they've given us, and they say draw a resonance structure. Now, to draw resonance structures, what I like to do is actually like to draw it a little bit different way. I see a COO minus. What that means to me, the only way it can form is as carbon attached to two oxygens. Okay, it's not going to be carbon, oxygen, oxygen. This right here is wrong. Do not do that. So never put that. Okay, it's going to be carbon, oxygen, and the other oxygen is also attached to it. But the big difference here is that one of them is going to be a double bond, and one of them is going to be a single bond. That's where the minus is. So minus means that, remember, they have an extra electron. That's why they're able to fill up like that. So instead of having to share again with carbon, which wouldn't be possible, it can kind of relax by itself because that's where the minus is. And now there's a reason why I did that, because resonance structures are structures to where the electrons are free-ish to move around that area. So now let's look at it through each part and see where it's actually possible for the electron to move about. So here, nitrogen literally has nothing to give, so there will be no resonance structure here that it can move. This oxygen, although it has double bonds and a single bond, this carbon really wants to keep that 4. Okay, so with that, there is really no space for the electrons to move. Carbon doesn't want to get 5, and carbon doesn't want to go down to 3. So there will be no resonance structure that can form here. Nitrogen, same thing, really wants that 3, doesn't want to double bond with anybody else right now, and even then the carbons and the hydrogen and the other carbon can't even accept that double bond, so that's no. So then here is just another CH2 bond. The only place here that can do resonance structure would actually be this right here. How, you ask, is that we could literally draw this same thing, but instead this took the double bond and these two electrons moved over here, making this the new quote-unquote negative one. Whoops. Making this a quote-unquote negative one now. And that is what they want as a resonance structure. So realistically speaking, we have drawn the first structure, but let me just draw both of them, and then that way we have our answer. And then I'll draw an extra picture just to show how the electrons are moving in that place. So really we have this okay, CH2 and COO. That is our first resonance structure. You can add in the electrons if you want and just keep consistent. I will, even though it does say you don't have to, but just that way you can kind of keep track a little bit easier. Okay, and then the same picture again, CH3 NH CH2 C. This one's going to be a single bond. Let me just draw a little bit better. Sticking out like that. And this one's going to be the double bond. So now the O is negative here. Okay. And this is what would signify our two resonance structures. Those are where the bonds are moving. Okay. And now, depending on how this, I don't know how that software works, but this is probably what is going to look like when they ask for that one resonance structure that would, I guess, represent these two together. Okay. is going to look like this. So same thing for everything else. Okay, and CH2. Now the way this is represented is that you still have these two lines to the oxygens, right? But it's going to be a dash. This is what represents the resonance structure, okay? And overall, you can just put the minus like right here, okay? Because this, just going to put it like right there to make it a little bit easier, because they're sharing that bond, okay? And there's an extra electron somewhere in that mess. So this is what's going to signify our resonance structure, and this is what the software is probably asking for you to draw. So with that, you're still going to have, just to make sure, 1 2 3 4, 1 2 3 4, but that quote unquote 5 6 is going to be rolling between the two right there, just like that, because exactly if you take out that 2 and put it as a bond, it's quote unquote there, but the carbon can only handle one at a time. So it's kind of always pushing, you know, that extra 2 electrons out, or yeah, in this case that's what it's doing. So this is what our resonance structure would look like in the end. So that is it for that question. Let's see how they did. Oh, well, there's nothing there, so I'm just gonna leave it here so you can pause as well, so that way you have an idea what you're looking for resonance structures. And just as future note, when you do see carboxylic acids that have gone through like losing that proton, that oxygen, it's now that basic structure, but more importantly, that is now free to form a resonance structure, because now you've allowed it to now be able to move across. If there was still a hydrogen there, so for some reason if we still had COOH, now there's no way for the electrons to move. The hydrogen is taken up, but now the hydrogen is gone, it allows it to jump wherever and keep pushing things out. So that's how we get our resonance structure. Okay, all right, and now let's see here what we